So anyways, yeah, I'm gonna need to have this here because I feel like it's not gonna be messy, but I don't want to confuse everybody because it's not easy. Okay, so I'm gonna start with fatty acid catabolism. Okay, if you go to the very beginning of chapter, y'all don't have computers? Okay, if you go to chapter 6 or 17, the very beginning, she talks about fats being digested and transported. So it says, I don't know, do you have your chapter 17 PowerPoint pulled up?
Yeah.
Yeah, fats digested and transported. I'm just going to find which slide this is on. Yeah, if you go to slide 6 in your PowerPoint, go to slide 6. It has a whole diagram, all right, of how dietary fatty acids are going to be digested and how they're going to be transported. This is also in correspondence, okay, to chapter 18, right, when she talks about LDL, HDL, chylomicrons, things like that, okay? So I'm going to start out with this, and then we'll get into it, okay? So when you eat a really fatty acid meal, right, fatty acid meal, a really fried meal, for example, right, the first thing that's going to happen, these are called dietary fats, by the way. Dietary because why? Get them in your diet. It's not that hard, right? So you get dietary. One second. Okay, dietary, right? Dietary fats. Okay? They're going to go through your system. It's going to pass your gallbladder. And the whole objective here is to get to the small intestines. Okay? The problem here is that you have these dietary fats, right? And they're like these globs. They're too big to be even absorbed by your small intestines. So what's happening here is that these like big droplets of fat, okay, from your meal are going to get digested, meaning that they're going to be emulsified by these things called bile salts. Let me tell you about bile salts, right? So what's going to happen first is that it's going to go to your body. It's going to essentially get touched by bile salts. What bile salts are, okay, what they do to this fatty glob of fried, they're just breaking it down, okay? What they do is that they create a micelle. Do you know what a micelle is, right? You know the idea of how we have detergents, right, where we have the center that is hydrophobic and the outside that's hydrophilic? That's the same idea of a bile salt. What the bile salt does is it gets released by the gallbladder as soon as you eat. And what it does is it releases those bile salts, it latches on to those globs of fat, and it breaks them down, meaning that I'm going to get these triacyl glycerols, okay, that are like compounded inside micelles, okay? That's going to make it easier for us to digest it, and then... Hey everyone, unfortunately my audio cut out when I was describing how you digest dietary lipids, so I'm going to pick off like where I left off, and I'm going to be going through this window and then switching back into this window so you can see me while I'm also describing and writing it down. So let's kind of start from the beginning just real quickly as a recap, and I'm going to use an example for this so I can better explain to you how you digest dietary lipids. So let's say I eat a huge piece of butter. You guys know butter has a lot of fats in it, right? So it's a big globule of fat. The thing is that my body has to digest this. It has to absorb it and break it down, right? So if I eat a butter, right, it's going to go through my esophagus, hit my stomach, and then hit my small intestines. That's just anatomy. It's not really something that you should know, but it's good to know. I don't think you should know for your exam. It's not in the slides that you should know that part, but it's going to hit your stomach. And what's going to happen here is that the stomach is not the place where you break down dietary lipids. It only does that about 30% of the time. So what does that mean? That means that really breakdown of dietary lipids doesn't happen in the stomach, despite the fact that it has the enzyme called gastric lipase. Yes, gastric lipase will break down some of that fat, but not as effectively. So instead, what's going to happen here is that this big butter is actually going to go into my small intestines. Everyone, you should probably really get this in your memory. The small intestines is the area where we will break down the dietary lipids. It will break down that big butter that I just ate. So just as a recap though, you just kind of heard me say gastric lipase. Lipase is a very important enzyme, not only in the stomach, but also in the small intestines. So if I have this big, right here, this big butter that's inside my small intestines, I have to get a lipase, right? I have to use a lipase on this to break it down into basically monoacyl glycerols, right? And now you might be wondering, whoa, Sophie, I'm like really confused. Like you just brought lipase out of nowhere. No, I didn't bring it out of nowhere, and I'm going to explain right now. First of all, you need to understand what a lipase is, right? A lipase, everyone, if I have a triacylglycerol, right? It's like this. The lipase, what it does is that it breaks it down into smaller, just basically monoacyl glycerols, aka fatty acids, right? I'm just going to denote it as that. It breaks it down into fatty acids. The problem here is that I have this huge fat. It has a bunch of triacylglycerols. It's just this big globule of fat. The problem is that the lipase can't actually attack this big globule, meaning that I need to break down that big globule into smaller globules so that the lipase can actually get in there and do its job. So what am I saying? What I'm saying here is that let's go down here. I need to take this butter, and what I need to make it into is smaller units of it, okay? Because right now I have a lot of triacylglycerols. It's too big. The lipase can't access it. So how do we get it, though, into these smaller units? Well, that's where this thing called bile salts comes into play. A bile salt, you should definitely know this. Bile salts have a hydrophobic portion, HB is what I'm going to call it, and a hydrophilic portion, HP. What the bile salts does, guys, is that it actually attacks this big globule so that it can create smaller units of it. Okay? It's trying to break this big thing down into smaller parts. That's really what the bile salt is doing. And with that, the bile salt, you should know, is made, so we can say that it is made in liver, and that it is stored / released from the gallbladder. So once you have your big dietary fat, that big butter coming into your small intestines, automatically your gallbladder is going to get a signal that says release the bile salts so that we can break down this big unit of triacylglycerols, all of these big triacylglycerols, big fatty goblets, into maybe just a little bit smaller triacylglycerols, right? We need smaller ones so that eventually this lipase can actually do its job. The big one is just not going to let the lipase come in. That's why we have the bile salts come in to break down that big globule into smaller units for the lipase to come in. And now I'm going to discuss emulsification. Okay, guys, so now let's talk about emulsification. Do not get this confused. Emulsification, everyone, is just the whole process that I described. The bile salts are just a compound that kind of aids in digesting those dietary lipids. So what am I saying? We already know that we have these globules. We have this big globule of fat, right? I just ate a piece of butter. And what's going to happen here is that my gallbladder, right, is going to get alerted, and it's going to send out these little bile salts to come in and attack it, right? By doing that, I automatically break into smaller units of the globule fat. Remember what the objective was. We need to break down that big thing into smaller units of fat so that the lipase can get in much easier. So right now, if it's too big, it doesn't work. This whole process that I'm describing to you is literally called emulsification, okay? What emulsification is saying, and this is where the details come in, why it's called emulsification, it's because if I have this big fat unit, right, what we need is that the bile salts to come in, and essentially they're going to create these micelles, okay? The micelles, everyone, is what is able to kind of separate that big fat globule into smaller fat globules, right? That's what it's doing. So it's having smaller units of it, which is exactly what I've said before. The only thing that I've added here is the aspect of the micelle portion of it. That's what emulsification is. That's emulsifying, taking that big portion of fat, emulsifying and creating a micelle with those bile salts. The bile salts create that micelle for smaller pieces of fats to be in them,
and then that allows the lipase to attack. You might have to watch this portion again a couple times to really understand what I'm saying, but it's this big fat unit that is able to kind of push into these micelles because that's the job of the bile salt. That's exactly what it does. Now, I had all these units of triacylglycerols. I mean, that's what a big fatty goblet does, right? A big fatty goblet of butter. And I'm just breaking them down into like 2 units, or it's just smaller units, really, right? And because of that, now I can essentially get my lipase, okay? Now my lipase can come in, okay? And it can break down the triacylglycerols that are inside these micelles, right? Because it's smaller now, and it can do its job into breaking down the triacylglycerol into just regular fatty acids. So now the lipase, my lipase, what it's going to do is that the tags that are inside the micelles, right? So these stuff right here, it's going to now take the lipase. Let's use a different color so that you can see what I'm talking about. It's going to take the lipase, right? Because the lipase can now access it better, okay? Because before it couldn't go through here. It's just too big, okay? So the tag is now going to go to the lipase. It's going to use the lipase, and it's just going to break it down into fatty acids, right? 3 of them, because there's 3. So it's going to go like this. Now I'm going to have this, this, and this. Once you get those monoacylglycerols, you get those just regular fatty acids, that is when your small intestines can essentially absorb them, right? Your small intestines can absorb it, or we can repackage it to go into the bloodstream. Because right now, what you've done, this whole process right here, has taken place in the small intestine so far, right? And our whole objective here was to break down this big thing, okay, this big piece of butter, into smaller units by emulsifying it with the bile salts to create these micelles. And then after that, I use the lipase because it can attack these smaller units better to essentially take my big triacylglycerols and make them into smaller units. The smaller units are what allow us to get either absorbed, or if we don't decide to absorb it in the small intestines, what we can do is package it and release it through the bloodstream to reach maybe your muscular tissues or your adipocyte tissues. And that's what I'm going to talk about, honestly, right after I kind of show you the image that Dr. Erb has in chapter 17, slide 6. So I'm going to pick up from there in a couple seconds. Okay, so now let me just real quickly go to Dr. Erb's image that she put in her PowerPoint, chapter 17, slide 6. So far, what I have told you, and just to go through this image with you, this is the butter that the person eats. It's going to go through their esophagus, go through the stomach, okay, hits the gallbladder, and then, it doesn't hit the gallbladder, but obviously goes, passes through, and then we get into the small intestines, right? The small intestines, that's where we're going to break everything up. As soon as this fat gets inside my small intestines, that is when we are going to release these bile salts, okay? So if this is my fat sitting inside, my bile salts are going to come in and attack it. As soon as it attacks it, okay, I'm going to form, obviously, the micelles, which is exactly what it says. It's going to form these micelles, which are smaller units of it, like that, okay? And because they are in smaller units, that, my friends, is what allows the lipase to attack it, to attack these smaller units of fat, to make the tag go into just regular fatty acids, or, and this is exactly what it is, these fatty acids right here, these smaller units of it, right? That's what it does, the lipase. So now that you get all those things, right, I told you that the fatty acid can either get absorbed by the mucosa of the small intestine, so it can get absorbed by the small intestines, or we can repackage it, okay? When I say repackage it, I'm saying that it's funky, but what's going to happen here is that as soon as you get and honestly, let's just go ahead and start from right around here, right? You got those three fatty acids, right? They can either get absorbed by the small intestines, I apologize for my handwriting, or we can repackage them. Guys, when we repackage them, what we're saying here is it's very interesting, because we just broke down tag to go into fatty acids, right? Well, what it's going to say is that if you want to repackage it and you want to send it to other places in the body through the bloodstream, okay, it needs a carrier. Triacylglycerols, fatty acids, they are too hydrophobic for the bloodstream. So what we use is chylomicrons. And chylomicrons only transport triacylglycerols though. And just now, we got it into a fatty acid. So if we want to repackage and send it to other places, so other tissues, right? We want to send it to other tissues. It has to go through the bloodstream, meaning that I need to take these fatty acids that I literally just broke down and I'm going to reconvert them. I'm going to reconvert them into triacylglycerols because I need to carry these stuff. I'm going to put a circle around it. I need to carry these stuff through the bloodstream, okay, to reach my target tissues, okay? Target, I'm just going to write target, okay? And this thing that is actually going to package it, that is actually going to, transport it through the bloodstream is called a chylomicron, okay? Chylomicron. And chylomicron, everyone, is only transporting tags, which is why you had to take the fatty acid that you just broke down to. And if the small intestine doesn't want to absorb it and you want to repackage it for somewhere else, it needs to convert back into a triacylglycerol so that the chylomicron can pick it up and transport it through the bloodstream. That is what I'm saying. Okay, so I basically have to use a chylomicron to go through the bloodstream and then receive it at my target tissues. So if I'm going to Dr. Herb's slide, okay, which is exactly what I just explained, it is saying that fatty acids and other breakdown products are taken up by the intestinal mucosa and can convert it into triacylglycerol. So what it's saying here is kind of something that it's basically the same thing I said, except for the fact that it kind of skips over the fact that small intestines can also absorb those fatty acids. What it's saying here is that it's going to kind of convert the fatty acids that want to get packaged into triacylglycerols and then pushed into chylomicrons to get into the bloodstream. That's all it's saying. Same thing I said. It's just one portion of it. So it's saying that you're going to take these single fatty acids and convert them back into triacylglycerols. The triacylglycerols are incorporated, obviously, with cholesterol and apolipoproteins into chylomicrons. That's a little bit of extra information. All you really need to know is that the chylomicrons is taking the triacylglycerols that you just converted back into to take it into the bloodstream. And honestly, yes, it has cholesterol and it has other portions, but chylomicrons mainly transport triacylglycerols. Okay, so hopefully so far this has made sense, but I'm kind of nearing the end. So now that you get these chylomicrons, okay, because the chylomicrons can transport those hydrophobic triacylglycerols through the bloodstream. Since the bloodstream is hydrophilic, it doesn't mix well. That's why it needs the carrier of a chylomicron. It's going to now go into the capillaries, okay? And the capillaries obviously go into our tissues, right? Capillaries to tissues, because you have these big blood vessels, capillaries, then you get to your tissues. So as soon as it reaches the capillaries, it says that lipoprotein lipase is activated by ApoC in this capillary, converts triacylglycerols to fatty acids, and glycerol. Guys, this is the exact same thing as when I mentioned the lipase in the beginning, right? That lipase that came in to break down the triacylglycerols into the fatty acids. That's the same thing here. What it's saying here is that as soon as you get, and let's do it right here, as soon as now I'm near the bloodstream, or let's use red. I'm in the bloodstream, okay? And I get to my capillaries, and let's say that this is the tissue that I'm trying to reach is an adipocyte, okay? Or let's just say adipose tissue, okay? So we'll say adipose tissue, okay? So I have this chylomicron, and it has my triacylglycerol inside, okay? In order for the adipose tissue to kind of get this triacylglycerol, we have to use the lipase that is inside the capillaries, okay? It's going to attack this triacylglycerol, and it's going to then form just fatty acids, obviously, and then obviously it also makes the glycerol backbone, but we know that glycerol backbone can be pushed back into glycolysis as glyceraldehyde 3-phosphate. If you don't know what I'm talking about, I believe that is also in chapter 17 in how to catabolize triacylglycerols, just as a backdrop for your information. But really, I'm going to take these fatty acids and the adipose tissue can pick it up. And that is exactly what happens, right? So the fatty acid can go into an adipocyte or myocyte, and eventually we can either store it, we can oxidize it as fuel, meaning that they can do beta oxidation on this fatty acid and make ATP out of it, or again, re-esterified for storage. So you have lots of ways. Once you get these chylomicrons and they're in the capillaries, you need to break down that triacylglycerol back into fatty acids so that the tissue can absorb it itself. So you kind of see that really it's important to get it down into that single unit of a fatty acid so that these tissues can better absorb it, like the small intestine, like the myocytes or the adipose tissue, adipocytes, right? They need that smaller version of it. But when you have those tags that are like right here, like the tag that's here and that it's in a chylomicron, that's just mainly for the transport of it, in essence, prior to the capillaries, prior to it reaching the capillaries. So hopefully this makes sense, and I've explained this fairly easily. I mean, I just say one more thing. I mean, the whole process is just this. I have a big fatty butter, okay? It's going to go into essentially a micelle, right? The micelle is going to have this triacylglycerols in it, right? It's a smaller unit of fat. It's not as big as this big one, right? Then after that, I'm going to use my lipase, and my lipase is what? Well, the lipase, I'm going to do lipase is going to break it down into fatty acids, right? Now, if the fatty acid doesn't want to get absorbed by the small intestines, well, I'm going to push it into a chylomicron, okay? The chylomicron is then going to reconvert it into a triacylglycerol. Then after that, if I get to the capillaries, so now I'm at the capillaries, and let's say that it wants to go to an adipocyte, an adipocyte to that specific tissue. What can happen here is that it's going to use another lipase, which we'll put in purple again, another lipase to break down the triacylglycerol inside the chylomicron that is in purple, and then it becomes another fatty acid, and then it reaches my target tissue. And sorry, that's really bad handwriting, but that's just the essence, everybody. So hopefully the digestion of dietary lipids makes way more sense now.
I guess what I'm going to focus on, glycerol catabolism is very easy in my opinion. All we're saying is what? A triacylglycerol, okay? Right? You have this big triacylglycerol, right? I told you, lipase it, right? Meaning I break it apart, I get the glycerol, and then I get 3 fatty acids, right? She says, but you can do something with that glycerol, right? What can you do with it? Tell me.
Convert it to acetyl-CoA. Or is it? Yeah, I think it is.
Glyceraldehyde 3-phosphate.
Or that.
Okay, so you're gonna convert it into glyceraldehyde 3-phosphate. And she did ask you guys today in your problem sets that if you have a triacylglycerol, she gave you those 3 fatty acids and she gave you the glycerol backbone, and she asked you to basically find the amount of ATP and NADH made in that, right? Okay, you have to be aware of how much ATP you use. You use means you subtract, right? How much ATP you make, add it. How much NADH, you add it. FADH, add it, right? People forget about the ATP being used. I saw so many people today, like, they had the they forgot to consider, okay, the ATPs that are used. And it doesn't even stop there. There's a lot, in my opinion, okay? So what I'm saying is that when you're going from glycerol to GAP3 dehydrogenase, not dehydrogenase, just GAP3, right, glyceraldehyde 3-phosphate, how many ATP, how many NADH are made? Or how many are used and how many are made?
I think 1 ATP is used.
Yeah, right? So minus 1 ATP. How many NADH are made? 2, right? 2 NADH are made?
Just 1.
I think it's 1, yeah. So we'll say plus 1 NADH. You don't stop here. You keep going, right? You do glycolysis. You get pyruvate. Pyruvate goes to acetyl-CoA. Acetyl-CoA goes to citric acid cycle. Electron transport chain you don't really need to worry about because you already convert all your NADH, all your FADH2, right, by 2.5 and 1.5. You've already considered it. Right? Makes sense? Like, I'm speaking, but I think I'm making sense.
Yes.
I'm not going to touch on this because you went over it in class. Doesn't make sense for me to do that. Pretty redundant. But do you see what I'm saying? Using, making, that's all I was trying to say. Okay. The next thing I'm going to touch first of all, where does beta oxidation happen? Yeah, mitochondria matrix, right? So the problem here is that when we say the mitochondria matrix, a lot of people are just thinking that only the short fatty acids are getting through, right? They're just getting through. Short fatty acids. That's wrong, okay? It's not this. This is not going through to the mitochondrial matrix. That does not happen. You cannot have a fatty acid going through the mitochondrial matrix. Any fatty acid that you have, any fatty acid, if it's long, if it's short, if it's branched, whatever, you need to convert every fatty acid first into fatty acyl Co A. Everything, okay? You have to put it into fatty acyl Co A. Long, short, whatever, right? Because a lot of people think that you only convert it for the carnitine shuttle. No, you have to do it for everything. The carnitine shuttle is just different because we have a really long fatty acyl Co A. Regardless, it has to be converted into this so it can flow through, okay? Let me ask you, what's the enzyme for this?
Fatty acyl Co A synthase.
Synthase? Or is it synthetase?
Synthase.
It's synthetase. Yeah, it's synthetase. So there's a difference, yeah.
Just a quick question, you have to convert this every time.
Every time. If you want to do beta oxidation, it has to get pushed into fatty acyl Co A. Long, short, medium, whatever. It has to.
And that's just for beta oxidation?
That for beta oxidation, yeah. Because if you think about it, actually I'll show you in a second. Even when you look at her slides that talk about beta oxidation, none of them are in this form. They are actually always in this form. Right? When you start beta oxidation, you're starting like this. And that's because of you converting it to fatty acyl Co A to go through the mitochondrial matrix. If you don't convert it, it's not going through. Long, short, medium, small, whatever, okay? So what's the enzyme for it? Fatty acyl Co A synthetase, okay? Listen, there's a difference between synthetase versus synthase. That's why I asked you that. Synthase uses ATP. Always. Any enzyme you see that says synthase, okay, is going to use ATP. Mark my words every single time. If you have synthase, it does not use ATP. Think about citrate synthase. Oxyl acetate plus acetyl CoA uses citrate synthase to make citrate. They don't use ATP for it. Not at all. But now, if I'm going to succinyl CoA to succinate, I use succinyl CoA synthetase. And that's where I use the GTP in citric acid cycle. You have to know these words, okay? It's going to help you for the future, okay? Fatty acyl CoA synthetase, okay? Do not forget here, I saw it today. People forgot that you have to use an ATP for it. Converting from fatty acid to fatty acyl CoA requires 1 ATP. Do not forget this. Because the thing is that as soon as I get this triacylglycerol, I've broken it down, right? I have a triacylglycerol, I break it down to the glycerol, and I break it down to the free fatty acids, right? One of the fatty acids, okay? Let's say one fatty acid, right? This is the one we're talking about. One of those fatty acids, before you can even start the beta oxidation, because I saw every single person just do the beta oxidation. No, you need to do this. You need to convert it into the fatty acyl CoA and then do the beta oxidation. Taking this step before is going to eliminate all your issues on the exam. If you miss that 1 ATP, you're going to get it wrong on the exam. You can't forget this, okay? So I get the fatty acyl CoA. What's the difference then between long fatty acyl CoAs versus short fatty acyl CoAs? What's the difference? Long versus short. So I have a fatty acid and I made a fatty acyl CoA. What's the difference between short fatty acyl CoAs? Long fatty acyl CoAs are going to use the carnitine shuttle. fatty acyl CoAs are gonna just diffuse right across the mitochondrial matrix to do beta oxidation. You need another chair?
No, I'm good.
Are you sure? Okay. Okay. I'm just wondering, why did it take you guys that long to give this answer? Can you be honest?
Said I watched lectures.
That's true. Okay. Is there anyone else? You didn't want? That's fine. Okay. So, as soon as I get this fatty acyl CoA, it's ready to go into the mitochondria, right? So I'm ready to go into the mitochondria, long or short. The problem is that these long ones are too big to go through. If they're too big to go through, we use a shuttle, which makes sense. I mean, you're using a shuttle because it's too big. If it's short and if it's small, less than 12 carbons, okay? If it's less than 12 carbons, I'm just going to diffuse right across. I'm going to diffuse right across. I'm going to go ahead and do beta oxidation. Easy, right? So, can anyone explain the Carnitine Shuttle to me? I'm going to show it to you. Can I erase this? Okay. This is going to be a really ugly picture, but if you draw these stuff out, it is so hard to ever forget it, okay? This is like my mitochondria, okay? It looks a little wonky. I'm just saying that this is my outer membrane. This is my inner membrane space. And I'm calling this my inner membrane. And I'm calling this my matrix. Okay? Or wherever the matrix is. Okay. Do you understand it? Where I'm going with this? So, what happens is that I have my fatty acid, goes to fatty acyl CoA now, right? So it looks like this. S-CoA, right? R group, right? So what's gonna happen here? Too big, can't go through. I'm gonna use carnitine. Carnitine is a shuttle. It's just attaching onto it, getting it inside, then releasing it again. That's all it's doing. So this is carnitine. That's carnitine, okay? I have this thing, it's gonna go through like that, okay? The CoA is gonna come off of it, and this thing is gonna attach and it's gonna become like, let's make it like this. Does that kind of make sense what I just did? The fatty acyl CoA is coming to the first carnitine. We'll call it carnitine 1. Okay? What it's going to do is that it's going to release the CoA group. And it's going to release it, obviously. So if this CoA group comes off, something needs to take place of it. The carnitine is going to take place of that, right? Because that's how you get it inside. That's how we start the transport process. You need to take the CoA off, and you need to put the carnitine on. Now what this thing is going to do is, it's going to go through this transporter essentially. I'm not a good artist, I'm sorry. Okay, it's going to go through this transporter, to which we call a transporter apparently. It's not even called a name. Okay, so what's going to happen is that now this thing with a carnitine is going to be easier to flow through. Okay, so now it's going to come in through, and it looks like this. The R group, because it's fatty acid, and the carnitine is right here, right? The thing is that I told you to start beta oxidation. What do you need to have? Come on.
Fatty acyl CoA.
Yes, God. If this has a carnitine on it, that doesn't make any sense, right? You brought it in, right? You took off the CoA group because you need to bring it in. I put a carnitine on it, goes through the transporter. I have the fatty acid, whatever, the R group, but it's on a carnitine. I need to take the carnitine off to regenerate what I started with, because that is when I do beta oxidation. So what's going to happen here is that this thing is going to add a CoA onto it, and it's going to release the carnitine, and and it's going to regenerate your fatty acyl CoA. Does that make sense? Say, yes, I understand. Yeah. What the point of it is that, so if this thing is too long, I guess maybe I'm going to use the carnitine to push it in, to attach it. It's mobile enough to get it inside, right? Once it gets inside though, I need to attach the CoA onto it again to do actual beta oxidation. When I attach the CoA, it automatically releases the carnitine. The same idea where the carnitine took the place of the CoA group, right? The same way that CoA fell off and carnitine came on is the same idea that carnitine comes off and CoA comes back on. That's what it is, okay? That's literally it. Are we good? So now, yeah.
Where does CoA?
CoA, where does it come from? Well, they're just regular coenzymes, so they could be just coming from anywhere, with all honesty. They could, I mean, there are other reactions that are happening that are releasing CoA and stuff, so if it's in the matrix, maybe it could be the CoA that comes off of succinyl CoA to make succinate, you know? So maybe that comes in and attaches there. Everything is regenerated. So now you have this, start beta oxidation. Okay, let's do beta oxidation now. What's the steps? I have an easier way to show you this, and it'll make, okay, if you want, you can memorize the slide. That's up to you. I'll show you the way I learned it to make it faster, okay? So, yeah, it's gonna be interesting, okay? So I get the acyl CoA, right? Start right here. Acyl CoA, okay? The first step, there's 4 steps in beta oxidation, right? Tell me at least the names of them. Tell me the names, like oxidation, hydration. Like, y'all, you guys know thiolase, right? Okay, that's fine. I'm gonna do it then. So what's happening here is the first step of beta oxidation. And the objective of it is to make an alkane to an alkene. We're gonna make an alkene, meaning we're gonna make a double bond, trans double bond. But before I even talk about all that stuff, I'm just gonna write it in a way that makes more sense, okay? First step, we call this step oxidation. Okay, slides are gonna say something different because I'm showing you what I learned to make it easier. In the first step, what do you make? FADH2, right? That's the first step. The second step, we call this hydration. Why do you think we call it hydration? It's a joke. Say water. Yeah. Right? Third step is what? Another oxidation. What does it make? NADH. What's the very last step? We call it a thiolase. And what do you think you make?
Oh, Acyl.
Yeah, you know what I'm talking about. What do you think you make? What's the end result of beta oxidation? You get an acetyl CoA group every single time. An acetyl CoA group, which is how many carbons? 2 carbons, right? But remember the acyl CoA that you started with? It's just going to be the acyl CoA but with 2 less carbons, because that's acetyl CoA. Y'all be writing? I'm going to explain it now. I just wrote down, this is a really easy way to remember beta oxidation, okay? I didn't write the enzymes. You should probably know the enzymes. But just for basic starters, the first step is oxidation, okay? All it's saying is that acyl CoA is going to be oxidized, okay? When you oxidize something, it means that you're taking off hydrogens. When you go from an alkane to an alkene, you're losing hydrogens, right? How do you think you make that double bond? Because you have to get rid of hydrogens, and then you collapse them, right? So in the first step, you're oxidizing, which means that FAD becomes FADH2, right? So this gets reduced. but the actual compound is getting oxidized. When we say oxidation, we're talking about the actual metabolite. We're not talking about this because this gets reduced. So don't give me some like thing saying that you got confused. No, you shouldn't be confused at all. Okay, you're in biochemistry. So you have oxidation. This is the step where we go from an alkane to an alkene, right? Oxidized, right? You lost hydrogens, made an alkene. Now, the next part is what? You add water. Why do you think you add water? Why? Why do you think you add water? Look at, there's an image in your thing as well. I don't know what slide it's on, but it's there.
Make alcohol.
To break it. You're basically, in step 2, you're adding water to break the original double bond that you had. You give an OH to the beta carbon, and you give an H to the alpha carbon. What am I trying to say? I'm saying this is that if this is a beta carbon, this is my alpha carbon, okay? And that's a double bond, right? We're in this step right here. We just made the double bond. When you add the water, what's happening here is that she says, just add the OH. Remember let's do this. Okay? She's saying that when you hydrate it, this is the beta and this is the alpha. When you hydrate something, you get rid of the double bond. So what she's saying is if it's H, O, and H, right? You're gonna add the OH up here. Don't forget the H that's on the bottom. And all you're gonna do is add the other H up here and the other H there. Do you see what you just did? You just broke the double bond, right? Makes sense. It's a hydration reaction. You add water to break it. So then after that, what's gonna happen here is that you're gonna use NADH to make H plus. That's just oxidation reaction in a sense of you lost another hydrogen, and what's happening here is that if H and H are going away, right? This is just for you to see. It might not be scientifically right. My man's falling asleep. Are you okay? I'm sorry. Okay. What's happening here is that the H's that we're talking about here are just these ones. So if those goes away, if those H's go away, all that's gonna happen is this. Do you see this? Do you see what's happening here? Oxidation, because you lost the 2 hydrogens that were right here, and you got that. Do you see I'm writing? Do you see what I'm saying? What do you think a thiolase does? What do you think it does? Thiolase.
Takes the time.
You're close. You're close. So, what's gonna happen here is that this S. Oh God. I don't know if she's gonna ask this on the exam, to be honest, but maybe you could remember this. The S in the Co A is going to attack this, and when it attacks this is amazing. Okay, it goes like that, goes like back down, and then it expels. When you add the Co A, it attacks the carbonyl. When it attacks the carbonyl, all it's saying is that you're breaking the bond right here between C beta and Ca alpha. And that's why you get this and this. Maybe you don't see it, but this is supposed to look like this, by the way. Right? You see what I'm talking about? This is the acetyl group that we're talking about, the acetyl Co A group. When you add the thiolase, it breaks the acetyl Co A off between C alpha and C beta. It's just carbon 1, carbon 2, carbon 3. It's breaking carbon 2 and carbon 3. That's what the thiolase does. That is the objective of beta oxidation. Does that make sense?
Yeah.
Yes. Okay. If it doesn't, that's okay. You go over it yourself. I'm just kidding. So, if that's what you're talking about,
I didn't know those figures.
that's been there the whole time. I just was focusing on alpha and beta from your slides. Yeah. Okay, that's fine. Take your pictures. Yeah, what's up?
What was the last thing that was broken off?
So, yeah, this kind of looks a little messy. So, what's happening here is that maybe you should write this down yourself. Let me just write. The sulfur in this Co A group is nucleophilic. When it's nucleophilic, it's going to attack an electrophile. from organic chemistry, what's an electrophile? The carbonyl, right? This carbonyl right here. So I'm just gonna write the rest of it real quickly so you can see what I'm talking about. So what's happening, okay. What's happening here is that this nucleophilic sulfur, okay? The whole objective of beta oxidation is to break off and make an acetyl CoA. The acetyl CoA gets broken off every single time between the alpha carbon and the beta carbon. Every single time it gets broken off there, okay? That's why you have that carbonyl made, right? From in this oxidation step, you make that carbonyl. The reason why is because it becomes electrophilic. This nucleophilic S is going to come in and it's going to allow for the cleavage process to happen. When you attack it, this bond goes up here. So what it's saying here is that I'm going to add the S CoA for you to see, right? That's what's happening, right? But now remember, it looks like this now, right? You made a tetrahedral intermediate. How many times have I told you guys about a tetrahedral intermediate? Every time you get a tetrahedral intermediate, something's getting cleaved off. And that's exactly what I'm saying. The alpha carbon and the beta carbon are consistently getting cleaved off to make 2 carbons of acetyl CoA. So, right here, these lone pairs, right? This is gonna drop down. If this drops down, right? There's too many bonds around carbon. This is gonna release and go there. So what happens here is now, I get the fatty acyl CoA group, which is right over here, right? This whole, as soon as this breaks off, it looks like that. And obviously you're gonna get an H here from somewhere in the environment. That's just how it works, right? And you're gonna get the acetyl CoA, which is this. This is the acetyl CoA, right? And this is going to be your fatty acyl CoA group. The CoA is right here. Do you see what I'm saying? I'm sorry, it got messy. Do you see it? Do you see it? Yeah? Okay, cool. Let's go ahead and, can I go to the next step now? Or we understand? Yeah, what's up?
This might be a tough question, but it's always going to attack the beta carbon, right?
Yeah, it's going to consistently attack the beta carbon because you're always trying to break alpha and beta every single time because that's 2 carbons away. That is an acetyl CoA, right? Okay. I don't think there's much left in, actually, I'm going to keep this here because now I'm going to show you fatty acid synthesis. This is just backwards. Fatty acid synthesis is just backwards. I'm going to show you. So, really quickly, slide 26, do not worry about slide 26. She told me that you don't need to worry about slide 26. If you're wondering about it, you can ask me, but you probably are not going to wonder about it.
Of lecture 17?
Yeah, lecture 17. 26, you're not going to need to know it. So, before I go through this, do you prefer if I can talk to you, or do you want me to write as I talk? Which one works better for you?
Right, as you talk.
Write as I talk? Okay, cool. So, when you talk about fatty acid catabolism, what are your end products? When you talk about fatty acid catabolism, what are your end products?
Breaking it down.
Acetyl CoA and then the acyl CoA group, right? And then she went through the lecture today. How many times do you have to go through the beta oxidation to break it down to each acetyl CoA? Yeah, that's pretty simple, okay? So, when we talk about fatty acid anabolism, fatty acid anabolism is what? What do you think? Anabolism is to create stuff, right? So we're making stuff. Whenever you make stuff, okay, it requires some sort of electron carrier, right? So NADP plus or NADPH, right? And it also requires acetyl CoA. So if you think about it, whoa, I don't know what happened here. 1 second, place. Acetyl CoA plus fatty acid. Whatever, you get the point, okay? So what's happening here is that this is just a backwards reaction. When we talk about fatty acid synthesis, it's just backwards. That's it, okay? But before I even talk about this, before I even tell you how it works backwards, there's a preparation step, okay? You have to know this. I don't know, man, mine was different. But when we're talking about the preparation step, we're talking about making Malonyl Co A. What do you think the difference is between Acyl Co A and Malonyl Co A? What do you think? What's the difference? Yeah, there's just a CO2 group on it. That's it. That's the only difference between Acyl Co A and Malonyl Co A. The real question is, how do you make it? What's the enzyme? Acyl Co A carboxylase, ACC, right? You had it in your lecture today. We said that if I'm talking about acetyl ACC, Acyl Co A carboxylase, okay, is going to make Acyl Co A adds a CO2 to make Malonyl Co A. I'll show you what it looks like. Ready? It just looks like this. Add a CO2. How do you think you add the CO2? How do you think? If you know what to say it, we can go faster. Yes, biotin, right? So you add biotin, right? The biotin cofactor moves the CO2 like this, like a hand, like a lysine arm, right? It moves the CO2 and it just puts it right here. Oh, don't forget, it also uses 1 ATP. Think about the arm, it has to move. The arm has to move, it needs ATP for it. Okay? So, all of a sudden, I'm gonna get something like this. What's the difference? Just added a CO2. That's it. Okay? You need Malonyl Co A for preparatory step, but also when you add 2 carbon units each time to synthesize a fatty acid. So what does that mean? I'm going to hold off for a second. In catabolism, you break it down each time. By how many units? How many carbons do you break down each time in beta oxidation? Say it. 2. You break it down each time with 2 carbons. So the same idea, it's not written here, but I'm speaking it. The same idea for fatty acid synthesis is adding 2 carbons each time, okay? But before you can start adding those 2 carbons, preparatory step. Now I'm gonna get into that. So you see how Malonyl Co A is made, right? You understand that to get Malonyl Co A, you need Acyl Co A, right?
Yes.
Keep it in your head. I'm gonna erase it down. Oh shit, my bad. There is an enzyme. It's called fatty acid synthesis or synthase, right? It's called FAS. FAS has different types. There's 1, there's 2. We're going to talk about FAS1. FAS1 is found in vertebrates, okay? What does that mean? Oh my god, vertebrates, what? Okay, it doesn't even matter, it's just people like us. We're humans, we have a spine, okay? So, FAS1 has 7 domains. And it also has 7, aka 7 active sites. I'm going to do an active site. If you go to slide 8, go to slide 8. When you go to slide 8 of chapter 17, you will see that there is a big subunit thing, right? And it has KS, MAT, DH, ER, KR, ACP, and TE, right? You see it? You count all of those, it's 7. So what does that mean and why should you know it? Easy. I'm going to quickly write it down, okay? It's KS, right? It's MAT. What's the next one? What's the next one?
ER.
What's the next one?
AR.
Next one?
ACP.
TE? TE? Okay. In each of these active sites, they have a job. The job is going to be doing which step of fatty acid synthesis? There's 4 steps in fatty acid synthesis, right? 4 steps, but you have 7 domains. So, tricky. What it's saying is that some domains are used for the same step. So what I'm going to tell you is that there's 7 domains, right? And there's 4 steps in fatty acid synthesis. I'm going to keep this here, and I'm going to go quickly to fatty acid synthesis. I'm going to show you the steps right now, because now I'm going to connect where each of these steps are happening on FAS. Does that make sense what I just said? Fatty acid synthesis happens in here, FAS1. The 4 steps are happening inside here, but it happens in either one of these 7 domains. You need to know which step is in which place, right? I'm going to show you. What's the first step of fatty acid synthesis? What's the first step? It does, but you don't use the same enzymes. Yeah. Condense. So you condense. Yeah, you condense it, right? So let's quickly write this, okay? What's the starting cofactor? What's the starting reactants for fatty acid synthesis? What is it? What do you start with?
Malonyl Co A.
Malonyl Co A. Yep, you start with it. Don't worry, I'm going to get to it in a second as well. Malonyl Co A. What do you generate here? Is there any generation here when you start with Malonyl Co A? No, it's not. It's a preparatory step. I'm going to get to it in a second. Prep. Remember I told you the preparatory step is really, really important before you start it? I'm showing you that right here. This is the preparatory step. I will go through it in a second. I just need to write down all the fatty acid synthesis so you know where everything is happening. It won't make sense for me to just hit one thing and not talk about the rest. So well then, what's the very first step of fatty acid synthesis? Condensation, right? Not condensation, condensing, right? So we're going to condense it. It's condensation, right? That's what I thought. Okay. It's condensed, right? When I think about condensation, I think about water leaving, okay? So when you condense, Co A is going to leave, okay? And so is CO2. In the second step, what do you think happens? Exactly. Reduction. It's the opposite. I'm going to show you in a second. It's going to make sense. When you do the reduction, what's happening here is that you're making NADP+, right? The reduction is the metabolite. The NAD+ is the one that gets oxidized, right? If this gets oxidized, right, it lost the hydrogen, then that means this thing got reduced. That's why we say reduction. These are talking about the metabolites, not those, okay? What's the next step? What's the third step of fatty acid synthesis? Dehydration. Right? So what's happening? Water leaves. And what's the very last step? Another reduction. Can you look right now at those two and tell me that it is backwards? It is. Look at it and analyze it for 10 seconds. Just look at it. No, 20 seconds. Look at it. Do you see it?
Yeah.
Easily, right?
It's backwards and opposite.
Exactly. It's backwards and opposite. Meaning that thiolase broke it off, right? You got the acetyl Co A and you got the fatty acyl Co A when you added this enzyme, right? Or this cofactor, right? S Co A. When you added S Co A, it broke it off. When you take Co A out, you condense it. Where you separate it here, you condense it here. Where you oxidize here, you reduce here. Where you hydrate here, you dehydrate here. And where you oxidize here, you reduce here. Eventually what happens is that I add 2 carbons onto my fatty acyl Co A, because that's originally what you started with, every single time. Right? Not even acyl Co A, because you don't have that. Fatty acid, right? Does that make sense? Are we good? Can you actually see how easy it is? It's so easy. But now here comes the thing. I talked about these 7 areas, these 7 active sites, right? On FAS1. Just so you know, all of fatty acid synthesis is happening on this enzyme right here, right? But each step is happening in either one of these 7 domains. I'm going to tell you which domains. Ready? In these first 3 steps right here, this is where the dehydration reaction will occur. This is where dehydration is. Okay? When we look at these 2 right here, this is where the reduction will happen. And just so you know, reduction happens twice, right? So it's clear that they all happen in the same place, right? It's not very much different, okay? And then of course, TE is a little bit different. TE is the releasing point. We'll call it when fatty acid is synthesized, right? When we've completed it, right? Complete. Now you're wondering, what is an ACP? What do you think the acyl carrier protein is? The acyl carrier protein, remember all of these are on FAS1. In her diagram, she has it like this, right? Like this. And that's the ACP, right? Right, that's the ACP? The ACP, okay, is like an arm. I say it every time, it's an arm. The ACP is an arm. How it works is, how do you think the fatty acid that you're trying to make is going to reach each part of these sections, right? It's on an enzyme. You have 7 areas, and you have to complete each of these steps. The ACP is swinging it onto each of these areas. If I want to do dehydration, okay, the ACP is going to swing it onto these sections. If I'm doing reduction, the ACP is going to swing it onto the reduction sites. Do you see what ACP is? Acyl carrier protein. It's a carrier, okay? It's acyl because you're making this big long chain, and it's trying to carry it to each spot on the fatty acid synthesis to complete fatty acid synthesis, right? That's what it's trying to do. Does that make sense now? You can see what we're trying to do? I told you about the preparatory step, right?
Yes.
What do you think preparatory is trying to do?
To create the Malonyl Co A.
Yeah, to create the Malonyl Co A. But really what the preparatory step is trying to do is that it needs to start, meaning that I need to start putting the first 2 carbons so that I can do the rest, right? Imagine you're starting from 0, right? But you need to have something there before you can add anything, right? It's like starting, you have to start at 0 to add 1, to add the next, to add the next. You can't just start at 5. It doesn't work like that, okay? So the preparatory step is starting from 0, having something there already to continue adding and doing the beta or the fatty acid synthesis. The preparatory step happens how many times do you think? Once for every fatty acid synthesis molecule you're making. Because once you prep it, you can continue adding. Don't worry about it, you do the preparatory step once. That's why it's called the preparatory step, okay? So, now I'm going to really quickly write the prep. You need to start with a Malonyl Co A. And you need to start with Acyl Co A. Right? You need to start with a Malonyl Co A, and you need to start with an Acyl Co A. Alright? This Acyl Co A is the only Acyl Co A in all of fatty acid synthesis that does not transform into Malonyl Co A. What does that mean? I'm telling you that the only Acyl Co A in all of fatty acid synthesis is used for the preparatory step. And that's it. After that, it's just going to be using Malonyl Co A to transfer every single 2-carbon unit. Do you understand what I'm saying? Okay, tell me where you're stuck.
So I thought the prep step was to make Malonyl Co A, but then also some Acyl Co A is maintained. Is that what you're trying to say?
Well, yeah.
Okay.
Right? This is the Acyl Co A that's maintained.
Yeah.
That is the Malonyl Co A that is being used for it, right? So, if this is my FAS, right? Fatty acid synthesis 1, right? The enzyme. And this is my ACP. In the preparatory step, you need to first have, what it's saying is that you just have this thing sitting here. Remember, you can't start from 5, you need to start at 0. Okay. What's happening here is that the ACP is going to have the Malonyl Co A on it. The Malonyl Co A is going to be the first compound on this thing. What does it look like? Looks like this. Oops. Make sure I'm drawing it right. Right? That's what it looks like, Malonyl Co A. Now, Acyl Co A is also going to be on this thing. It has to be there. Has to be there. Like it has to. So, I'm gonna put this a little bit lower so it has space, okay? It's right here. This is gonna be my S, C, okay? O, CH3. Right? That's just acetyl Co A. So this is my acetyl Co A right here, attached onto FAS1. And I have my Malonyl Co A. Okay? Do you guys remember those domains I told you about? The first domain that was the KS domain. Remember I told you KS? You wrote it down. I'm sure you wrote down KS. Yes, KS is where dehydration occurs. Yeah, that is where it occurs. But what you also should realize is that this fatty acid synthase, right? It looks like this. It has all of these stuff on it. Those are the domains. 1, 2, 3, 4, 5, 6, and then of course 7, right? It's there. That's where this thing is swinging in each one. Okay, so the preparatory step is saying that I have to put Malonyl Co A on ACP, and I have to start with acetyl Co A on here. What do you think happens in beta oxidation? What are fatty acid synthesis? You're adding 2 carbons each time, right? You're adding 2 carbons each time. This is the only time where you're going to take the 2 carbons and acetyl Co A and put it onto this chain. You're putting it onto the Malonyl Co A. Let me say something real quickly. As much as this is the preparatory step, okay, you're starting with acetyl Co A here, and these are the 2 carbon units that eventually get transferred here, and obviously CO2 gets pulled out, right? CO2 gets kicked off. I want to make sure I can see some people's faces get confused. Wait. I know some people understand, and I know that some people don't, so I'm going to help with other people who don't understand it. Look, the preparatory step is just this. This is the preparatory step. That's it. This is what you get. That's it. Preparatory step for any starting point of fatty acid synthesis, you start like this. Start like this. You have to have acetyl Co A. Now, the next part is this. Now, after you get this acetyl Co A here and you have the Malonyl Co A, now you can start fatty acid synthesis, and this is where you do the condensation. CO2. Okay, CO2 leaves. What it's saying here is that this thing, what do you think is going to happen? What's going to happen is obviously the CO2 is going to leave, right? That's the CO2 group we're talking about. CO2 is going to leave. And instead, now what it's going to look like is something like this. ACP, right? I have my S, C, O, CH2, and of course I have my, oh, sorry guys. CH2, I have my CO, and of course CH3. Do you see what I just did? Do you see what I'm talking about?
Yes.
That's the first step, condensation, right? And then the next step would be reduction. I am not going to go through steps 2, 3, and 4. Why? Because it's exactly the same thing as this, but you're doing the opposite of what happened. Okay? I'm not going to go through it. It's just opposite. If you really want to go to a slide that helps, I recommend going to slide want to see it, go to slide 24, or sorry, slide 14. Slide 14 will show you what happens after you've done the condensation reaction. This is condensing right here. This was condense. First step. The second, third, and fourth are very easy. It's very easy. It's just this backward. That's why I'm saying, if you know how to do beta oxidation, 100% you're going to be able to do this one. Just know what it is forward, then you can figure out how it works backwards. No joke. People just get stumbled on right here, what's happening, why it looks like this. Think about beta oxidation, okay? Backwards, and instead it's on some carrier or whatever. See what I'm saying? It's just on a carrier, and it's just backwards. Don't get confused. But I want to say something. So let's say I complete my fatty acid synthesis, and eventually I get this compound, right? Eventually I added the 2 carbons now, right? Eventually I finished the first round of fatty acid synthesis, add 2 carbons, and it looks like this. Right? It looks like that. Can I ask you a question? Which two carbons on this thing were from the Acyl Co A? Which one are they? Yes, ma'am. That's exactly what it is, right? So it's saying here that in one round of fatty acid synthesis, right, you added these 2 carbons, right? So that means that these carbons were already here, right? These are the first 2 carbons from where? Malonyl Co A, right? And these are the 2 carbons that got added from what? Okay, if I want to do the next round of fatty acid synthesis, the thing that gets added here is not going to be Acyl Co A anymore. You use Acyl Co A only once. Now every time that you add 2 carbons, it's going to be Malonyl Co A. Okay? Are you lost? Say it. Say I'm lost. I don't care.
Just want to make sure. So the Malonyl Co A will be attached where the Acyl Co A was originally to the tube looking.
Yeah. You only use Acyl Co A in the first step because there was nothing there, right? Meaning that I had this CO2 here, like I couldn't. The only thing that was going to be able to attack it really was this Acyl Co A. Now that you passed the preparatory phase and you did that first stage, right? You had the preparatory with the Acyl Co A. If I want to do the second round of fatty acid synthesis, this thing is already prepared. It's prepared for you. Do you see a CO2 on this? Because I don't. I don't see a CO2 on it. So you're not going to need to add another Acyl Co A. You're going to have to use Malonyl Co A now. Malonyl Co A to transfer 2 carbon units at a time again. It's the same idea of adding the 2 carbon units here, right? Acyl Co A added 2 carbon units. Those carbon units are right here. Instead, we're going to use Malonyl Co A. We're just going to use a different compound for it. Why not? Just add the 2 carbons. Why not? I think that's all I have. Right? Does it make sense? What's the net reaction? I want to ask you this. What is the net reaction, and it was in your thing already, what's the net reaction if I have 16 carbons? 16 carbon fatty acid, what's the net? Tell me what's the net. Huh? Okay, let's do this. How many Malonyl Co A are used to make my 16 palmate? Or palmate? 7. Okay, so then how many Acyl Co A were used?
8.
How many of those get converted to Malonyl Co A?
1.
Hold up. What? 7.
Oh wait.
One of them stays the same.
Yeah.
Okay. Seems like you guys make sense to me. See what I'm saying?
I think so. All of them, except for one, go through what we had already discussed with the biotin step.
Yeah. Ooh.
Oh, sorry. By biotin, I just mean the carboxylate.
So let me just say something before you go. You have 8 Acyl Co A, right? And how long is a palmate? 16 carbons, right? Okay. The first two carbons that are sitting on the ACP are from Malonyl Co A. So automatically I can tell you that it's better if I write it. One acetyl Co A went to Malonyl Co A. That's the preparatory step, right? To put it on. Oh man, I erased it. Okay. To put it on the ACP. The next one I had was just the regular acetyl Co A, right? This is the preparatory phase, right? What happened here was what? Only these two carbons are the one that attached onto here, and the CO2 left, right? That was the first round. So this is 2 and 2, right? If I start with 2, I start with 2 Malonyl Co A. It's on ACP. And I have the 2 carbons here, right? Technically it's 3, but you know CO2 leaves, so we're just gonna call it 2 for now, okay? CO2 left. No, CO2 didn't leave. I'm not gonna say that to you because you're gonna be confused. There's 3 carbons right now on it. There's 2 carbons on acetyl Co A. What happens here is, right? Does this make sense? Yeah? What's happening here is the first step is condensation, right? So, if the first step is condensation, then CO2 leaves, right? Now it becomes 2 carbons, right? And these 2 acetyl Co A are gonna attach to it, right? 2 acetyl Co A attach. When 2 acetyl Co A, 2 carbon units are attached, that's 1 round of fatty acid synthesis, right? 1 round of fatty acid synthesis puts 2 carbons on it. And I just added the 2 carbons from acetyl Co A, right? So, this is from 1 round. So how many more rounds do you need to do 16 carbons? 7. You need 7, right? You already had these already here, right? You don't say 8. You already had the 2 there from the preparatory step. Transferring the 2 carbons is only 7 times. This was already there, so I'll add it once. Then I'll add it another time. Next, right? 2, 4, 6, 8, 10, 12, 14, 16. Count it. 1, 2, 3, 4, 5, 6, and then of course 7. Right? That was already there. Do not get that confused. Okay, now I'm done. Yeah. Wait, and each of these 2 carbons, which ones were they? All of these carbons, except for this one. Which ones are these? All from Malonyl Co A, right? These ones are all from Malonyl Co A. Only this one is from acetyl Co A. You're done. Now you can go. I'm done.
Rather small.